Okay, so consider this scenario. You're given some problem and you decided to use a machine learning model to solve this problem. You have some data, you take your data, you choose a model, you use a training algorithm to fit some parameters to your model. And then you test your fitted model using a test set that wasn't used to train the model. Okay. And unfortunately, the test set results are not very good. Now, my question to you is twofold. My questions are, what went wrong? I'm going to list all the questions and then you'll start supplying answers. What went wrong? So why did my model do poorly? How can I fix it? And the third and most important is I want you to give me an example of this type of problem from one of our previous lessons. For example, I'll give you one answer. Okay. So maybe what went wrong is maybe the loss surface was not so great and our training algorithm didn't converge. And we might fix that by, let's say, using a different training algorithm for example, one that varies the learning rate in a different way. And as an example of when we saw that, we can mention last week's notebook with collinear features. What are other examples of things that could go wrong with our model and examples of how we've seen it? If you don't know how to fix a problem, that's also okay. You can still mention things that might have gone wrong. Okay, so you were given some learning task, you trained the model, it's not great. Okay, so Ben says, results seem too good to be true. And Disha says data leakage. I think you're probably both getting at the same thing. Okay, so another possibility is, I'm going to kind of generalize here. And I'm going to say maybe there's a problem with the data. We previously spoke in week 1 about all kinds of data problems we might have. Right, so we listed a lot of data problems. Some of them were data leakage, but some of them were other problems. So maybe there's a problem with the data and we need to process data to fix the problem. And what's an example of seeing a problem with the data? Have we seen any example where there was some sort of problem with the data? So there are many examples here. One example we gave was, for example, the email scenario with potentially duplicate data. We looked at an example of a COVID chest X-ray with data leakage. Okay. Elena mentioned missing data. Okay, so many potential problems with the data. And these are all examples we've seen. So for example, in our Brooklyn Bridge situation, we saw there was some missing data. Okay, and I would say the fix involves not just processing the data, but exploratory data analysis to find the problem and then fix it if you can. You won't always be able to. Okay. What are other things that could have gone wrong with our model? Okay, so Ben says the model could be predicting based on features that should not matter. So let's say we need to, let's say we treat that as something separate from the data leakage problem. Let's say we say in order to fix that, we're going to just remove those features. Do we have any examples of that particular issue? Okay. So the beauty in the classroom case study. Okay. What else could have gone wrong? Let's think of examples that are not data leakage examples. So kind of more categories of problems. Yeah, Ahmed says when we fit a linear regression when we need a multiple linear regression. So that's a good example. I'm going to just say more generally, the model that we chose isn't capable of fitting the data. Okay. And to fix that, we would need to try a more capable model. And some examples we saw of that are, let's see if anyone started on the second homework assignment. Or let's say the example we did in class of a residual analysis on a multiple linear regression, where we had to add additional interaction terms, and we had to add some nonlinear transformations of the features. Are there any other examples of specific types of problems that we've seen so far? So if you propose something that went wrong, you have to give me an example of where we've seen it so far in class. Evan says, training didn't converge. That covers that we picked too high of a learning grade and skipped over optimal values, right? Yes, exactly. So if there's some sort of problem with the training algorithm or optimizer we're using, maybe we try a different one. Okay. Are there any other examples of problems that we've seen so far in this class? Okay. In the notes for this week, I asked you to read a little bit about a cubic model that was used several times last year to try and predict the future COVID cases, where various people tried fitting various linear basis function polynomial models to this data. And they claim to have very good results. For example, this one from some news organization in India claims a forecasting accuracy of 94% or 98% for two different models. But after the fact, their models turned out to perform very poorly. So the predictions of the model did not even come close to coming true. And I asked you to think about why did the models miscalculate so badly? So they seem to fit the data well, but they didn't. What happened? Is it one of the problems we mentioned so far? Or is it something else? So Ben says, okay, maybe there were features not examined by the model. Okay, so that would be an example of choosing a model that isn't capable of fitting the data. But if normally, if there were, let's say, features that were not used by the model, but that were important for predicting the outcome, then you would expect to see kind of very poor performance. You wouldn't really expect to see good scores. If there are a lot of important features that are not incorporated into your model at all, then you would expect your model to have good scores. You wouldn't, bad scores, sorry. You wouldn't necessarily expect your model to have good scores, but then fail to actually predict the future. Okay. Ahmed said maybe it used features that didn't matter. It's possible. So the main feature it used was, let's say, days since the beginning of the pandemic. So I think that's probably a feature that does matter. Does anyone have any ideas what went wrong here? Okay, so Michael said training and testing the model in the same data set. So that's an important point. Okay. When they did this analysis, it looks like they're just fitting a model to all of the data. They're not fitting a model on some of the data and then seeing how the model performs in the future. So if we were going to do that, let me see if I can annotate this. So suppose we would take, okay, this data, fit a model on that data, and then use a fitted model to predict the performance here. So that would be a better way to do it. But here, there doesn't seem to be any mention of doing that. It seems to be they're using all of the data to just fit what they're calling a model. Okay. What else could go wrong? Okay. So it didn't take into account different variants. So it's definitely true that I'm going to kind of generalize that answer. So it's true that the model they were using didn't really have an epidemiological basis. Right? There's no epidemiological reason why the spread of infection should follow this polynomial model of degree 6 or a polynomial model of degree 3 or degree 2. Okay. So it didn't take into account the epidemiological realities. Now, a machine learning model isn't necessarily an exact simulation of infectious disease spread or other things, but it should make sense, right, given whatever we know about the specific domain. So this is another example. The COVID chest X-ray data was also an example of that, of a situation where someone took a machine learning model, trained it to some data, and didn't consult with domain experts at all. So the domain experts, meaning the epidemiologists, can look at this and tell you, like, no, there is no way an infectious disease spread is going to follow this pattern. But they didn't do that. So one thing that's kind of interesting is I want to try and understand why, if it was such a bad model, so we listed lots of things it did wrong. It didn't predict, it didn't evaluate on test data, didn't have any epidemiological basis. It extrapolates into the future when they don't really have any evidence to support the idea that the future should kind of be a continuation of the past. But why, if it's such a bad model, does it fit so well? And Evan and Ahmad both have a part of the answer here. So the answer here is that if you allow an arbitrarily complex model and then put an optimization procedure on it and say, optimize this model for this particular data. Well, if you allow an arbitrarily complex model, you can fit any data perfectly. Let's take an example. So suppose I have some data set that looks like this. Okay. Now, suppose I'm going to allow an arbitrarily complex model. That means the model can have as many parameters. I can have a cubic model with like degree 100. If I allow an arbitrarily complex model, I can fit this data absolutely perfectly. So an arbitrarily complex model, okay, I can't draw perfectly, but I can fit the data perfectly even if I can't draw. An arbitrarily complex model could fit any data set perfectly. But of course, that doesn't necessarily mean it will fit some other future data perfectly. Right? So now suppose I have some new test examples. different color, different color. My test examples are pink. Suppose I have some new test examples. Now, these are perfectly fine test examples. They're clearly drawn from the same distribution as the training data, but the model doesn't fit them well. Right? So you can take an arbitrarily complex model and fit any data at all and have very, very good scores on the training data. That doesn't mean it will generalize to new unseen data. And that's also part of the problem of what's happening here with this cubic model. So they're taking arbitrarily complex models. There's no epidemiological reason why, let's say, the spread of a disease should follow a polynomial of order 6. But they're taking this arbitrarily complex model, fitting it to the data. And of course, if it's great, you can take a very complex model and fit any data. That doesn't mean it's going to be predictive of future data. So we have all these issues here. And I'm going to give an example here. So arbitrarily complex model can fit. Okay, so here my solution might be to use a simpler model. So I have all these possible reasons why my machine learning model did not behave very well. And they all have different fixes. How do I know which is the reason in my case and how I should fix it in this particular case? Can I try all of the fixes and just see what does well? So what if I try, okay, using a different training algorithm, doing some exploratory data analysis to fix the problem, trying all different subsets of features, removing those that are not relevant, try a more capable model, try a less capable model, talk to domain experts. Is that a good approach for when my model doesn't have the performance I want? Okay, so Braden is exactly right. Yes, I could do all that, and maybe I'll be done in about 10 years, right? So this is not a very efficient way to train, to fix a machine learning model. So in order to be efficient, we need to be able to identify what was the problem. So we need to be able to look at the result and see, hey, where did this problem come from? And then we know how to fix it, and we can target our fix to the specific problem. So that's what we're going to talk about today. Given a problem with a machine learning model, or given a machine learning model with a problem, how can we identify what the problem was and what really are the problems in a machine learning model more generally, and then how could we fix it? So let's talk about prediction error. Okay, so here is the premise of machine learning. The premise of machine learning is we have as training data a set of feature vector and label pairs. So the X's are the feature vectors, the Y's are the labels. And we want to fit some function f, and we chose our function f. And function f is parameterized by w. And then we're going to fit function f, and that means come up with some estimate for w, which we'll call w hat, such that y is approximately f of xw. So the goal of machine learning, or the premise of machine learning, is that we choose a function parameterized by some w. We fit the model, which means estimating w hat, such that the labels are approximately equal to f of xw. Okay, so that's the premise. Now, imagine that our data is sampled from some unknown true function. And we did this actually last week in our linear regression notebook. We had some data generating process that would generate data. Now, last week it was a linear regression data, but it doesn't necessarily need to be that. So imagine the data is generated by some unknown true function t, so that each sample y is equal to a function of the features, t, and that's an unknown function. We don't know what it is. And some epsilon I is applied to each sample, where epsilon is normally distributed, so it has zero mean, but some non-zero variance. And that epsilon is what we call some unknowable error. So this is stochastic error that no machine learning model can ever learn, right? It's like trying to learn the outcome of flipping a dice. So that's our premise so far. So we have, the goal is to fit a function. We have data generated from some true function. That's not necessarily the same as our function f. And then we want to minimize a squared error loss on some test data that was not used for training. We're going to define a test point. It's xtyt. And our goal is to minimize this quantity where this expectation is over all the possible test points, okay, and the noise, of course. So we want to minimize a squared error loss function. Okay, let's try and visualize that. Okay, so I want you to imagine there is some x, y data. So we're just going to imagine one feature because that's easier to visualize, but there can be many features in reality. And let's say we have some sort of infinite population of data. So we have this data generating process that generates data from some infinite population. So we never run out of data, essentially. Okay? There is as much data as you could possibly imagine. And from this infinite population of data, we're going to draw some training data. So we're going to randomly sample from this population, and that's going to be our training data. And then we're also going to randomly select a test point. So we have this infinite population of data generated from this underlying process. Okay. And the underlying process generates data according to T of x plus epsilon, where epsilon is this unknowable noise. It's stochastic noise, cannot be learned by any model. And the true function is unknown to us. Our goal is to take this training data, so the blue dots, fit some function f that's parameterized by w, so that y for the training data is approximately equal to the output of our function. And we want to do that in such a way that it minimizes the mean squared error for that test point. Okay. Now, what are the sources of prediction error in this scenario? So let's imagine kind of like a best case scenario. Okay. Best case scenario, let's see. Best case scenario, this is my true function. Okay. And so the green one is a true function, and the turquoise dashed line is my f of x. Okay, so we have t of x, f of x. Okay, and best case scenario, these are actually identical. Okay, so maybe t of x is equal to minus 10 plus 15x. And oh, look, f of x is also equal to minus 10 plus 15x. Okay. Is there any error in my model? What is the expected error for that test point? And here the expectation is over all of this, okay? So even though my model is exactly identical to the true function, right, there's still some error due to that stochastic noise. So even in the best case scenario, and the best case scenario is when f of x is equal to t of x for all x. Okay, so the true function and the model function are identical. F of xw. even in that case, we still have some prediction error due to the stochastic noise. So that's one source of error, the noise. Let's imagine another source of error. Okay, so suppose looking at this training data, you could see that we happen to have gotten like a few more samples that are above the line than below the line. So maybe like, 1, 2, 3, 4 samples that are kind of above the line and only 2 below the line. Right? So maybe when we estimate our parameters, just due to the kind of randomness of the training samples we selected, we're actually going to select this other line instead. So now I have a different source of error. What's the source of error here? Okay. So Evan said when splitting between the training and test sets, I want to be careful here because in this hypothetical scenario, we're going to say we're sampling our training and test sets from an infinite population. So yes, this is exactly right though. When we randomly sample this training set, our parameter estimates, so here this, let's say -7 and 12 are parameter estimates of our model, right? They come from W. The parameter estimates depend on the random draw of training samples, which are noisy training samples, right? So because of the random draw of noisy training samples, we might have some error in our parameter estimates. So you could imagine that the true function t of x has let's say, could be equivalent to f of x with, let's say, some true parameters wt. Right? So maybe there's a situation where, well, if we chose the right parameters, our true function would be exactly equal to the model. But because of the random sample of training data, our parameter estimate is not exactly correct. So our parameter estimate w hat isn't equal to the true parameters. Okay. So that's a second source of error. So the second source of error is that our parameter estimate is not exactly correct because of the random error in the training data. Okay. What else could go wrong? So what if my true function is not even, let's say, of this form at all? What if my true function is something like x to the power 3 plus x to the power 2 plus x plus 1? Okay, so let's try and draw something like that. Okay, so this is another potential source of error. This is a source of error called undermodeling. Okay. So maybe there is no parameter estimates in the world, so there's no possible W that can make f of xw equal to t of x, right? Here we have what's called undermodeling, which is a scenario where our model is not flexible enough to mimic the true function. As part of fitting our machine learning model, we assumed what's called a model class. Okay. A model class is a set of possible models we could fit parameterized by W. So here we assumed a model class. The model class is something like, okay, it could be 1 plus 1x, it could be 1 plus 2x, 1 plus 3x, 1 plus 4x, it could be -7 plus 10x, it could be -7 plus 50x. There's a very large set of possible models we can fit with our assumption of, let's say, W0 plus W1x. But in this scenario, the true function is not in the model class. So the true function is not one of the models parameterized by W that we consider. By the way, when we, let's say, train a machine learning model, there's a whole set of assumptions we make. And one of those assumptions is an assumption of the model class, so what that F should look like. And then this introduces what we call inductive bias into our model. So this is an example of inductive bias. Our assumptions about the model are not flexible enough to actually mimic the real true function. So those are some sources of training error. Now, what would happen if we used a model class that's too complex? Let's take this example. Okay. And let's say we used a model class that was like, okay, W0 plus W1 plus W2. And I'm going to put the functions out here, actually. Okay, so let's say we assume, let's say, a 5-dimensional polynomial model class. Okay, is this a bad thing? Let me get rid of some of this, let's say, some of these random points. So if we assume, let's say, this model class is the true function in the model class, is there some parameter estimate for W that could find the true function? So exactly, what if I said W5 equals 0, W4 equals 0, W3 equals 1, W2 equals 1, W1 equals 1, W0 equals 1. So in that case, the true function is in the model class, which means there is some parameter estimate for which f of x is equal to t of x. So why not just always use, let's say, very complex functions so that I don't have an under-modeling problem? Okay. Well, let's imagine I do this where there is no noise in the data. So I'm going to move this data. So if there's no noise in the data, then actually it would be safe to do that. If there's no noise in the data, then looking at this training set, I can imagine that the only function that would minimize the least squared error on this training set would in fact be if I would, set W05 equal to 0, W4 equal to 0, W2, W1, W0, all 1. Okay. So if there was no noise in the training data, I could use an arbitrarily complex model, and it would find the true function. It would just set the unnecessary weight parameters to 0. But because we do have noise in the data, when I use an overly complex model, add my noise back in. Okay, so with noise in the data, when I use my overly complex model, well, it's not going to find those zeros. It's going to find those zeros. It is going to instead just try and fit the noise in the data. So an overly complex model, if I have noisy training data, will try to find the parameter of values that are optimized for the noise that happened to come up in my training sample. So this is not going to work well. So this is actually an example of an error in our parameter estimate. If you think about it, it's very similar to the other situation we described before, which is no longer on the board, where due to the random sample of the training data, I come up with wrong parameter estimates. So let's say my parameter estimate for W4 should be 0, but maybe it will be 5 instead. Okay, so using a model class that's not complex enough is under modeling. That's bad. Using a model class that's too complicated is also bad because then we'll end up with bad parameter estimates. Okay. So in summary, what are our sources of prediction error? We have the stochastic noise that's fundamentally unpredictable. We have the parameter estimate error, which is due to the noisy training data and the random sample of training data we drew. And note that this also includes a situation where the model should have selected 0 coefficients, but didn't, right? So that's what we've been kind of calling overfitting. And then a third source of prediction error is when our assumed model class is not complicated enough, so under modeling. Okay. Now, although those are sources of prediction error, let's see if we can kind of formalize this discussion. So quantify how much of each type of error exists in our model. Okay. So this is what's known as the error decomposition for the mean squared error. Okay. Now, some notes here. You're going to see a lot of versions of this error decomposition. If you look at all the textbooks or if you look online, you can see a lot of different versions of it. And some of them kind of gloss over, let's say, what the expectation is over. Okay. So we're deriving the expected error for a test point. Now we're actually trying to think about an expectation 3 times over. Okay. So first, our expectation is over the sample of a test point. Right? So we're computing error for this test point, but then we want to take the expectation over any possible test point we could have drawn from this population. Then we're also interested in the expectation over the draw of the training sample. So we saw that some of the sources of prediction error were due to the random sample of training data we happen to pick. So when we quantify the expected error, we want to average out that effect by taking an expectation over the random draw of training data. And finally, we know that another source of error is a stochastic error, which applies to the test point. Okay. And we want to take the expectation over that also. So in our error decomposition, we're interested in taking the expectation over the test point, then also over the draw of training samples, and also over the stochastic epsilon t of the test point. But when we do this derivation, we're going to do it in 2 steps. First, we're going to assume that the training sample is fixed. So we know that actually the training sample is random, right? But we're going to first assume that the training sample is fixed. And so the expectation is not over both the training sample and the epsilon noise of the test point. The expectation is only over the epsilon noise. And we can do that. This is allowed because the epsilon noise for the test point is independent of the training data that we happen to sample. And so the expectation over both the training draw and the epsilon is equal to, let's say, the nested expectation. So we're going to first assume that the training sample is fixed, take the expectation over the epsilon of the test point, which is that stochastic noise. Then we're going to relax that expectation and take the expectation over the draw of the training set. Okay, so now that you know our approach, let's take a look. So we're looking at the expected mean squared error, or the expected squared error. Okay, that's this quantity here. Now, this gets very messy, so I've taken a little shortcut here. I'm denoting it as F, the output of the model for the test point, given our estimate of training data, our estimate of parameters W hat. And I'm denoting it as T, the output of the true function for the test point. Okay. Remember that the Y sub T, so the true value of the test point, is equal to T plus some epsilon. Right? And then our prediction is equal to the output of our model F. Okay. So we have F of xt for our parameter estimate W hat is Y hat of T. Okay. And the T subscript here denotes that it's for the test point. And then we have y of t, which is the y value for the test point, is equal to the true function plus some epsilon. So we have this expectation here. Now, in our expectation, I'm going to kind of group these two terms together. Okay, so imagine we have a t minus f plus epsilon, and I'm going to treat this whole t minus f term altogether. And remember that the expectation here is only over the epsilon. So the t minus f are actually constants. So I'm going to treat that like this and actually complete this square. So we have t minus f squared plus epsilon squared plus this 2 epsilon t minus f. And remember that because our expectation is only over the epsilon, we said for this part of the derivation, our training sample is fixed. And if our training sample is fixed, then our parameter estimate is fixed. So this is a constant, and this is also a constant. And so this part can come out of the expectation. It's just a constant. So we have this part out of the expectation. Next, let's take a look at this term. Okay, so this term is, okay, so the 2 is a constant, the t minus f is a constant, but then we have the expectation of epsilon t. But recall that epsilon is distributed with 0 mean. Sorry for my terrible handwriting. Epsilon has 0 mean. So this term becomes 0 because the expectation of epsilon t is 0. So that goes away. And we're left with this constant t minus f squared, or at least it's constant with respect to the expectation over the stochastic noise, plus the expectation of epsilon squared. What's the expectation of epsilon squared? So we said that epsilon is normally distributed with 0 sigma squared. And so the expectation of epsilon squared is just sigma squared. And this term is what we call the irreducible error. Okay. So the expectation over epsilon of the squared error is equal to this term, which we're going to call, well, we'll call the expectation over that term the reducible error, and this term, which we call the irreducible error. Now, the irreducible error is independent of the draw over the training sample. So in our next step, we're going to then take the expectation of this over the draw of the training sample. And this is not going to change. That's independent of that. So then we only need to concern ourselves with taking the expectation of this over the draw of the training sample. Are there any questions so far? No, everyone's following? Okay. So we're taking the, we're trying to derive the expected value of some error on a test point. And in the first step, we took the expectation with respect to the epsilon noise in the test point. In our second step, we're no longer assuming that the training sample is fixed. So now we're taking the expectation over the draw of the training sample. Okay. So we're taking the result of the previous step and taking the expectation of that over the draw of the same training sample. Now, remember that this epsilon squared is independent of the draw of the training sample. Sorry, the sigma squared is independent of the draw over the training sample, so that can come out of the expectation. This is just a constant with respect to the draw of the training sample. And then we can multiply out the square. So we have the expectation over the draw of the training sample of t squared plus f squared minus 2tf. Now, remember, t is equal to the true value of the function for the test point. Is this independent of the training sample? So the only thing here that's depends on the training sample is our parameter estimate. Our parameter estimate depends on the training sample. the epsilon sigma and the true value of the function for the test point does not depend on the training sample. So since the true value of the test point does not depend on the training sample, this can come out. And we're left with, let's say, this part here, which does depend on the draw of the training sample. And I'm omitting some, algebraic steps here. But eventually we end up with something like this. So we have the true value for the test point minus the expected value for the model. And then we take that squared. That's the first term. The second term is the expected value of the model output squared minus the expected value, the squared expected value. Okay, I can't say that out loud, but this is basically e of x squared minus e of x squared. Does anybody know what this expression is generally? This is a definition of variance. So by definition, variance of x is equal to expected value of x squared, where x is some random variable. The variance of a random variable x is equal to the expected value of x squared minus the expected value of x squared. Okay. We have this term that's equal to the variance of this random variable. And then finally, we have a sigma squared term. So let's talk about those terms. Okay. We're going to think about some hypothetical but impossible experiment. Let me just close this. Okay, and this experiment is going to help us kind of think about this error decomposition. So suppose we have many independent training sets drawn from the same process. So remember, we have this idea of kind of some underlying population of data from which we can sample as much data as we want. Okay. And let's say we take many random draws of training samples over this data, and we fit a model to it. Now, every time we fit a model, we're going to get a slightly different result. So maybe the first time I fit the model, I'll get something like this. Second time I fit a model, I'll get slightly different parameter estimates. Why am I getting different parameter estimates each time? Every time I fit my model, I get a slightly different line. Why? So I keep drawing from this underlying sample, this underlying population of data. And every time I draw a new random training sample, I get a new model with different parameter estimates. And the different parameter estimates are due to the different samples of training data. Right? So each of these lines represents a different model from a different training set. But again, all the training set is drawn from the same underlying distribution, and all the models are fitted from the same model class. So each of these lines represents a different set of parameter estimates. And now I'm going to take the mean of all of the lines. So for every single data point here, for every possible x, I'm going to find the output of each model and take the mean of that. And then I get this line here. Okay. So this line here is the mean model. Does that make sense? It's what would happen if we trained infinitely many models on many different samples from the training data. Okay. There's a question here, would the error decomposition be different for a different loss function? So the general procedure would potentially be different, but the sources of prediction error are the same. So you'll end up with something very similar. And there are some derivations for different loss functions in some of the books. Okay, so we have this hypothetical experiment where for many independent training sets drawn from the same process, we estimate parameters, estimate some value of test points, and then we have the mean over all of these models, which is this kind of heavier line here. Okay, let's take a look at that error decomposition. The first term in the error decomposition is a difference between the true function. So let's put the true function back here. It's a difference between the true function and the mean model. Okay, so the mean model is this kind of heavy dash blue line. The true function is the green line. So the first term in the error decomposition, which it was called the bias, tells us over all the different samples of training data, or let's say over all the different samples in the population, what is the difference between the true value and the mean model? Okay, so looking here, we could see okay, so there's this like difference here between the green line and the blue line. That's the difference between the true value and the mean model. Okay. And this is called the bias. What does this tell us? Informally, it tells us to what extent the model is systematically wrong. So here, the issue is not necessarily that the model has a wrong parameter estimates, because we expect that, you know, over the mean of many random training sample draws, it's going to come up with, you know, the mean will kind of arrive at the right parameter estimates. But there's still some systematic difference between our model and the true function. What's the reason for the systematic difference? Why is there kind of a systematic difference between the mean of all of our blue line models and the green line? Okay, so this is an example of under modeling. So in this example, we have bias because our model is not complex enough to approximate the true function. And it's often the case that if our model is not complex enough to approximate the true function, then we'll have bias in our model, which means the systematic error where there's a difference between the mean of our model, or when I say the mean of the model, I mean the mean of many models trained over many training sets, and the true function. The next term we said is, by definition, the variance of f over d, right? We said the expectation of a random variable squared minus the expectation of that random variable squared is, by definition, the variance of the random variable. So here, the second term in this error decomposition is the variance of the model prediction over the random draws of training sets. Okay. Does this depend on the true function? Does the variance term have any relationship to the true function? Okay, so no, it does not. So t does not appear in the second term. The variance term depends only on the individual models. So each of these little blue lines that we trained are individual models trained over different training samples. And the mean model, which is this heavy blue line. So we're taking, let's say, the variance of the model predictions over D relative to the mean model. So the variance term here refers to how spread out are all of these individual model lines relative to the mean model. If the models were less spread out, meaning each individual model was kind of more similar to the mean model, then we would say the model has less variance. If the models are more spread out, then we say the model has more variance. So this has nothing to do with that true value. It's only about how spread out are the individual models relative to the mean model. Informally, what does this tell us? So if you look at, let's say, how much does an individual model vary from the mean? Remember, the differences between the individual models and the mean are due to the random draw of training data. So informally, this tells us how much does a model output depend on the training data. If we had a model where it didn't depend on the training data at all, we would expect to have very little variance. Let's look at an example of that. So suppose my model was X. Okay, suppose my model is, okay, this is my true function. Green line here is true function. And suppose my model is a constant. Okay, my model is f of x equals 2. Okay. If I train this model many times over different random training samples, are my lines going to be very spread out? Okay, so no, my lines are not going to be spread out at all, because here my model is a constant, doesn't depend on the training data at all. Right? So if I train this model many times, I'm just going to get the same line over and over and over again. I'll have no variance. Do I have bias? Okay, so this model has plenty of bias. There's a big difference between the mean of the models and the true functions, but it has no variance at all. And we're kind of getting the idea that when a model is less complex, it has lower variance. If the model is more complex, it has less bias. Let's look at the third term. So the third term was the irreducible error that we said. And if we go back here to this example, and let's put back in our training sample, sorry, our test sample, the red dot is a test sample. So the irreducible error is just due to that epsilon noise. And this is something we can't really ever get rid of, and we don't really expect to. Okay. So it's a difference between, let's say, the data point and the output of the true function. So to put it all together, we said the expected test point error is equal to the squared bias, where the bias is the difference between the model function, the mean model output, and the true function, plus the variance over the draw of the training samples. The variance over the draw of the training samples tells you how spread out are individual models relative to the mean, or how much does the model output depend on the draw of the training data. And then finally, we have the irreducible error, which is the difference between the point and the true function. Okay, so those are our error terms. Now, this is kind of a more generalized derivation for mean squared error. But there are, let's say you'll find something similar for other loss functions. So you can find derivations online for, let's say, a 0-1 loss function where the score is 1 if the prediction is exactly correct, or 0 if it's not, or some other loss functions. Just the derivation is a little more complicated. And you can also kind of derive this more specifically for specific models. So after this meeting, I'm going to post some notes online about the derivation of the bias and the variance for our linear regression model. And I'll ask you to read those notes. So those tell you something about how the bias and the variance will vary with things like the number of parameters of the model, the number of training samples, and so on. Okay, are there any questions on this derivation or on this concept? Okay, so we might have this intuition based on what we just saw that says that, oops. We might have some intuition based on what we just saw that changing the model to reduce the bias increases the variance, or changing the model to reduce the variance increases the bias. So why is that? So let's take this example here. Right? One model that we could potentially have is this constant model. Right? Does our constant model have high variance or low variance? Okay. The constant model actually has zero variance. The constant model just says output 2 over all times. No matter how many times you train that model, it will have exactly the same output, so no variance. Does it have bias? So this model has high bias. There's a big difference between the mean model and the true function. So let's make this model more complicated. So the first model we considered was f of x w equals 2. Now let's consider, okay, let's call that model A. And let's say model B is f of x w equals w0. This model is just the w0, which if we find the w0 that minimizes the mean squared error, it's going to be the mean of the training data. Now, I'm going to ask you to think about model A and model B, and we're going to do a quick poll. Which model of these two models considered here, where model A is a constant and model B is W0, which will be mean of training data, which model has more bias and which model has more variance? Okay, take another couple of seconds to vote. Okay. So a small majority said that model A has more bias. Let's look at this. So model A is a constant. Now here I showed, let's say, model A being right in the middle of the data. But let's say, okay, so maybe the data really goes up much higher over here. I'm not going to draw that. Let's say model A, the constant value ends up being down here. Okay. Now, suppose I'm going to then train model B on many examples of the training data. So let's say one time I might end up with this value, this line, because I selected these particular training data examples. Okay, maybe another time I have These training data examples, make them purple. Okay, so then I might end up with a line over here. Maybe a different time, I have these particular training data examples. Okay, so I have a line over here. Okay. And then I'll end up with some kind of mean line. Let's make my mean line be this. Okay, so this is my mean line of all of these different potential fitted models. Which one seems to be closer to the green line on average? Okay, let's make their example a little easier. Let's say that the prediction of the constant model is up here. Okay, let's say 2 is over here. Okay, so which model is closer to the green line? Is it this constant model up here, or is it the model that takes the mean of the training data? Okay. The mean of the training data is closer to the green line, so it has less bias. Okay. What about the model? Which model has more variance? So if I train the constant model many times, I'm going to get the same one every time. Right? So there's no variance at all. If I train the mean model, I'll have a slightly different model for each subset of training data that I sample. So the mean model has some more variance. So here we can see that getting a little more complicated made our model have less bias but more variance. Let's try another example. So now model A, the mean model, and model B is a linear model. Okay. So if I train model B on different subsets of training data, I might get a bunch of lines. Let's draw some lines. And maybe one subset of training data will give me this line. Another subset will give me this line. Another subset will give me this line. Okay, do I have more bias or less bias? Is the mean of all these models closer to or farther to from the green line? Let's try this again. Okay, so you can go ahead and vote in the poll. Okay, so here model A is a mean model and model B is a linear model on one feature. Okay, take a few more seconds to vote. Here model A is a mean and model B is linear with one feature. Okay, so here we seem to be in agreement that model A, which is this line here, has more bias. So the mean of the mean model is farther on average from the green line. Model B, which is a linear model, gets kind of closer to the green line most of the time. So it has less bias, but it has more variance. So, if you kind of extend this line out, you can see that you might end up with kind of a very wide spread. So as we make our model more complicated, we start to see more and more variance, but potentially less bias. Let's imagine like a really complicated model. So let's imagine a really higher order polynomial model. Here's a version for the magenta training data. This is what I'd get if I trained on the blue training data. And sorry, I'm very bad at drawing. Here's what I would get for the purple training data. So the more complicated your model gets on average, the more it depends on the training data, which we said is what contributes to variance. But overall, it then also tends to have less bias. So we have this trade-off here. Now I'm going to put a big fat caveat here, which is this is kind of a classic view of the bias-variance trade-off. And recent results suggest that this is only kind of part of the picture. But at least for the first part of the class, we're going to work with this. So we have this idea that as our model complexity increases, we first reduce the bias. So if you start off with an extremely simple model, like a constant model, then you have very high bias and high error as a result of the high bias. Now, as you increase the model complexity until it starts to be very similar to the true function complexity, then you reduce the error because you're reducing your bias. What happens if you make your model more complex than the true function? Well, as you make your model more complex than the true function, then you start to get that variance, which is overfitting essentially, and your error increases. What kind of error increases? Well, when you have high variance, right, we said with a model with high variance, the training error is very, very small. So as you increase your model complexity, the training error will continue to decrease. But the test error, which is the expected error for that test point, will start to increase. So we have this kind of trade-off here. And remember, this is only a kind of part of the picture, but it works for now, which is as you increase the model complexity, your training error will always go down. Your test error will first start to go down because of reducing the bias, and then it will start to go up again because of increasing the variance. So there's this trade-off here where in order to get small error, you want to end up at this point right here. So you need to get model selection right. You need a model that's not too flexible, not too complex, but it's flexible enough. How do you choose a model that's flexible enough? Okay, we're going to talk about that next, but first we're going to take a 60-second break so that everyone can kind of decompress a little bit. All right, see you in 60 seconds.